Okay, in this section, we are going to review sigma notation. We're also going to take a look at some sigma properties and some new sigma formulas that will be very helpful in the next section when we get into calculating the area under a curve. Okay, so just recall that a series is just the terms of a sequence being added together. So it's a sum is what it calculates. So in pre-calculus 12b, I believe we looked at this example. Here we have the numbers 1 plus 2 plus 4 plus 8 plus 16 plus 32. Those terms are missing, plus 64. If the terms are on their own with commas between them, we call it a sequence. If there's plus signs between them, it's known as a series. All right, so this series has an a value of 1. The first term is a 1. And it's got an r value, a common ratio of 2, because we're multiplying each term by 2 to get the next one. So 1 times 2 gives me 2, 2 times 2 gives me 4, then I would go times 2, 8, times 2, 16, times 2, 32, times 2, 64. We could figure out this general term, this formula here, by replacing our a value with a 1, the first term, our r value with a 2, the common ratio is 2, and our exponent would be n minus 1. Now, in the textbook, they replace the n's with i's in this section, so I'll do the same. So 1 times, so it'd be 2 to the I minus 1 times 1. That's not going to change. It just gives you 2 to the power of I minus 1. And to write that in a more compact form, we learned that we could use the Greek letter sigma, which means that indicates a sum, or the sum of. Here's my general term from 2 raised to the power of I minus 1. And we're going from an I value of 1 to an I value of 7. So that means if I put a 1 in here, okay, sorry, a 1 in here, 1 minus 1 gives me 0, 2 to the 0, the first term would be a 1. If I put a 2 in, 2 minus 1 is 1, 2 to the first is 2. That's the second term. This is the third term, so put a 3 in for I. 3 minus 1 is 2, 2 squared is 4, and so on. All the way up to 7. Okay, 2 to the 7 minus 1, or 2 to the 6th, would give me 64. So this symbol is read the sum of the terms of the sequence given by the general formula, Ti equals 2 to the I minus 1 from I equals 1 to I equals 7. All right, so we're just replacing the n's with i's. Here's another example. This one is an arithmetic sequence, or an arithmetic series, with an a value of 1 and a d value of 2, a common difference of 2. Remember, to find the common difference, we subtract term 2 minus term 1, term 3 minus term 2, term 4 minus term 3, and so on. If I do that, I get 2. When I fill it into the arithmetic formula, a plus n minus 1 times d, I fill a 1 in for a and a 2 in for d, and I get my general term to look like this. When I simplify, I'm left with 2 times I minus 1. So let me just replace this n with an I. And this is all review from pre-calculus 12b. Now, here are some properties which we're going to look at, which will be helpful in the next few examples. The first one is if you're finding the sum of just a constant term here, well, it doesn't matter what your n value is up here. The simple rule is you're just going to multiply this n value by whatever that constant is. So in this example, my n value, which is the upper bound, or this number on top of my sigma symbol, is 5, and I'm going to multiply it by the constant 4, and that would give me 20. This series would have a sum of 20. If you have the next property, so in this case, c is just a constant. So when I have the sum of the terms of the series 3i from I equals 1 to 4, I can really just write this as 3, times my sigma symbol from I equals 1 to 4, and I just have an I back here. Now this might look weird now, but I'll show you when we get into replacing these. This is actually a linear formula that we'll use, and it'll be very helpful in the next section. Here, if we're finding the sum of something like this, we can break it into monomial summations, they're called, so into two individual sums. So it would be the sum of, from I equals 1 to n of 4i squared plus, and then I'll have the sum of, from I equals 1 to n of 7i. Now if that was a minus sign in between here, I just change that to a minus sign. Now I can use property number 2, so I can take my constant 4 and I can write it in front of the sigma symbol. I can take my constant 7 and I can write it in front of the sigma symbol. The I squared would stay on the right and the I would stay on the right in this case. And there we have it. So those are some properties of sigma that we'll use in this section. So use the basic properties of sigma notation to express in terms of monomial summation. So in this example, I'm going to expand the binomial 3i minus 2 first. So it's to the power of 2. So this would be 3i minus 2 times 3i minus 2. That's going to give me 9i squared when I multiply this by this, minus 6i, minus another 6i, so I'd have minus 12i, and then plus 4. Now, I can write this as individual or monomial summations. So it would look like the following. My first term would be 9i squared minus my second term is a 12i, and my third term is just a 4. It's a constant 4. Now I'm going to pop the constant 9 out in front and the constant 12 out in front here, and I end up with the following. Now remember, this 4 is not going to go in front because we need, it's just a constant. I'll show you what we'll do with this in a moment. Okay. But this right here is my linear sigma formula. This right here is my quadratic sigma formula. And this right here is a constant, this guy. So we know what to do there. That's this property or this rule right here. I just multiply the the n, my n value on top by this constant 4. So in this case, it would just be 4 times n. But here's what I was getting at. Okay, there's the linear formula. There's the quadratic formula. And here is the cubic formula. There was no I cubed in that last one, so we didn't need to worry about it. But this is what it looks like. So we're going to use these guys to kind of help us sort things out. So in that last example, all right, wherever I see this from I equals 1 to n, the sum of the terms generated by this, the formula I can replace this whole thing with this. I can replace this whole thing with this. So this is what I would end up with. And if I scroll this up, or I drag this up, so there is my quadratic formula. I replaced that whole symbol, all right, with the quadratic formula. I replaced this whole symbol here with the linear formula. And when it's just a constant, we know to just multiply by n. Now, we didn't have to do this, didn't have to go this far in this question. This question was actually finished at this point right here. Okay? Because it only asked us to express them in terms of monomial summations. So there is a monomial summation, a second monomial summation, a third monomial summation. But this is kind of where we're going when we end up trying to simplify this. Okay, we can take the sigma formula, replace this with its appropriate sigma formula. And that's what this question will do. We'll go further. We'll take it a little further. So, for starters, I could write this as two monomial summations. So from I equals 1 to n of 3i squared minus the sum of from I equals 1 to n of 2i. Now I can pop the constant 3 out. So it'll be 3 times the sum of, so there's my quadratic. And I'll pop the 2, this constant 2 will come out in front of the sigma symbol. And we'll just leave 1 I. So I have, once again, this is the quadratic sigma formula, and this is the linear sigma formula. So I can replace this whole thing right here with my quadratic sigma formula, which is n times n plus 1 times 2n plus 1 over 6. So again, you make this connection. If it's an I squared after the sigma formula, you're using n times n plus 1 times 2n plus 1 over 6. So I get n times n plus 1, 2n plus 1 over 6 minus 2 times, if it's linear, okay, to the first, and I to the first, that's why we say linear, it's just n times n plus 1 over 2. N times n plus 1 over 2. Remember, if it's a constant, just there's no I here, you would just multiply by n, take the number behind or after the sigma symbol and multiply it by n. And if it's an I cubed, it's basically the same as the linear, you just multiply it to the power, raise it to the power of 2. So now we'll clean this up. So I can do this. 3/6 would reduce to 1/2. I can do the same here, but I'm not going to bother because this then now you can see they both have a denominator of 2, which will make it easier to simplify. So in this case, I have n times n plus 1 times 2n plus 1 over 2. All right, 3/6 reduces to 1/2. 1 times all of that on top would just be those the same thing, n times n plus 1 times 2n plus 1. Here I'm going to have minus 2n times n plus 1. I'll multiply the tops. Bottom by bottom gives me 2. Since they have the same denominator, the move is to subtract the numerators. So it'll be this numerator minus this numerator over 2. And you might be saying, well, what can I do with that? Well, think about this for a second. How many terms are in the numerator? The answer to that question is 2. This is one term. This is the second term. I can factor out, I can take out a common factor and simplify this. Look, this term has an n, this term has an n. This term has an n plus 1, this term has an n plus 1. So I can take out a common factor of n times n plus 1. What it means to take out a common factor is to divide both of the terms in the numerator, or all of the terms in the numerator, by the common factor. If I divide this term right here by the common factor, I would be left with 2n plus 1. If I divide this term by the common factor, think about this, negative 2n times n plus 1 divided by positive n times n plus 1, that would just leave a negative 2. And it's all over 2. When I simplify this bracket, the square bracket, I've got 2n plus 1 minus 2. Positive 1 minus 2 would give you a negative 1. I'd have 2n minus 1. And that whole expression can be simplified to the following. Okay, this right here is equal to this. These are going to be important in the next few videos when we start calculating the area under a curve. I'll just show you the answer to example 4. I don't want to really get into it for sake of time of the video. All right, but I'll kind of explain it. Here we're going from not from 1 to 20, but we're going from 11 to 20. So you'll notice what I did was I went from 1 to 20, and then I subtracted from 1 to 10, because really this would be missing terms 1 through 10. When I simplified it, I ended up getting 4,505. Okay, so here I use an n value of 20, here I use an n value of 10. Don't forget, at this point you distribute the negative over both of those terms. You could get the same answer by just filling an 11 in, a 12 in, all the way up to 20, and you would end up with 4,505 as well. What we really want to focus on in this section, however, are these 3 sigma formulas, because those are what we are going to use in the next 2 videos. You can try these questions for homework.